video, we are going to discuss about atomics. But before we move further, let's take a very simple example and try to understand how GPU threads execute that instruction. So let's say we want to do a equals to a plus 2, where a is some volatile variable. Now, let's say this is the order of execution of instruction. Not that we are breaking a equals to a plus 2 into multiple small assembly level instructions, because that's what happened at the assembly level. So now let's say the thread 1 executes these three instructions first, and then thread 0 takes the command to execute these three instructions. Uh, Not that we are assuming thread 0 and thread 1 are not from the same verb, which is definitely very essential condition to execute these two instructions in a different, in an arbitrary parallel fashion. So now first thread 1 is going to read A from the global memory and puts it into thread 1 register. Then it's going to add 2 to the value stored in the thread 1 register. And then it's going to store a value of A from the thread 1 register back to the global memory. So not that A is updated to 2 now. Now, thread 0 is going to read A from the global memory, which is 2 in this case, puts that value into the thread 0 register. So thread 0 register will have A equals to 2, and then it's going to add 2 to the value. Now, the thread 0 register would have A equals to 4, and then it would store the results back into the global memory, where the global memory would be updated with A equals to 4. But are there any other possibilities? Definitely, yes. So let's say this is the order of execution, because thread 0 and thread 1 are from different verb. They can have arbitrary order of executing the instructions. So let's say this is the new order. Both the threads read the A from the global memory at the same time and load the value into their respective registers. And then they add 2 at the same time. So the thread 0 register would have 2, and thread 1 register would also have 2. But the global memory is still having A equals to 0. Now, let's say thread 1 executes the instruction first. Now thread 1 updates the global memory with A equals to 2. Now the thread 0 gets executed and update the global memory again with A equals to 2. So it's basically overwriting it. Now you can see that A is equals to 2 in the end. It's not 4. So it's not the result we expected. That's where atomics can be really useful. Atomics are permitting operations whose effects are either visible fully or none, but never partially. They work both with global memory and shared memory. So let's say this is the instruction again. So now these instructions will be tied together and can be think of as a single instruction, as shown here. Now let's say A equals to A plus 2 is implemented using atomics. Now what would happen? We would have these three instructions which are tied together, and then these three instructions which are tied together. Thread 0 and thread 1 are going to execute these instructions in an arbitrary parallel fashion. This time, the instruction would get pushed to a queue. So since we are not doing the normal A equals to A plus 2, rather we are using some atomic operation, it's going to get pushed to some kind of queue, and that queue is gonna get popped out in a very sequential manner. So we are going to have introduce some kind of sequentiality, and because of that particular sequentiality, we would always get A equals to 4 in the global memory. There are several variants of atomics you can find in CUDA. You can read CUDA documentation for that. Some of them are atomic guess, atomic min, and atomic add. You can find other operations as well in CUDA documentation. Please check that out. Uh, Major application of atomics includes that it prevents data race when multiple threads are accessing same memory location, and these can be used to implement global barrier as well. But one of the main drawback of atomics is it introduces sequentiality. Let's say we want to find the sum of the array. Now, for finding the sum of the array, if we use atomics, then we would have to do n operations if n is the size of array, because each of the addition operation is going to push to some kind of queue. But if we use other strategies called reduction methods, in which we do parallel sum of several small subparts of array, then with that reduction techniques, we can achieve the same sum in log n time. So definitely atomics can sometimes introduce sequentiality and decrease the speed up, which we can get with other techniques. Thanks a lot.